Okay, let's look at section 6, kinetics and equilibrium. Which statement best describes the reaction that you see happening here? We have a single H together forming diatomic hydrogen. So we know a bond is being formed. So that means these two are wrong. And when we break things, we have to add energy in. So when we form bonds, it releases energy. If the heat of reactants are 45 kilojoules, the heat of products are 35 kilojoules, and the heat of the activated complex is 95 kilojoules, what is the activation energy of this reaction? So down here we are sketching it. So I'm a diagram person, so I'm going to skip ahead and sketch this first. Okay? So 10, 20, 30, 40, 70, 80, 90, 100. Okay, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay, so the heat of reactants are 45. The heat of the products, 35. So 45, so that's 45 is reactants. Activated complex is 95. So up like this to here. And the products is 35. So that's here. So then come down like this. Okay. What is the activation energy of this reaction? Well, activation energy goes from reactants to the tip top. So that is going to be 95 minus 45, which is 50 kilojoules. Adding a catalyst will lower the activation energy. And I want to word this a little differently by providing an alternate pathway. Likewise, adding an inhibitor will raise the activation energy by providing an alternate pathway. Okay, I don't really like the language there, so we kind of use a little bit different. So if we're looking at this, if we were doing a catalyst, we would start the same, end the same, but our activation energy would be lower. If we added an inhibitor, so this is a catalyst. If we added an inhibitor, we'd start the same, end the same, but would actually take more activation energy. So that would be an inhibitor. Don't usually talk about that one as much, but just in case. The heat of reaction. So that is products minus reactants. So products is 35 minus reactants is 45. Negative 10 kilojoules, which is right because this is exothermic. Starts high, ends low. It should be negative. Okay. Okay, so then just real quick, exothermic reactions look like this. Endothermic reactions look like this. We can find out if a reaction is exothermic or endothermic by looking at table I, because at the bottom it tells us a minus sign indicates exothermic. So everything that's minus is exo, positive is endothermic. Okay? All right, so for this reaction, what must be true about the rate of boiling and the rate of condensing? Well, if it is at equilibrium, rates must be equal. Concentration's constant, rates are equal. All right, so here's a reaction. If N2 is added, which way will the equilibrium shift? Right. If temperature is decreased, it shifts toward it when it goes this way. If pressure is increased, okay, pressure only depends on gases. Everything is a gas. So I'm going to look at both sides. Here's the arrow. I have 1 gas molecule and 3 gas molecules, so 4 total gas molecules. On this side, I have 2 total gas molecules. So if I increase the pressure, it's going to want to be on the side with less gas molecules. So right, If H2 is removed, it's going to go toward that, so it's going to go left. If NH3 is added, it's going to go left. All right, and when it goes left, so let's look at the second part of this. What happens to the concentration of NH3? It decreases because it's going this way, so use up this and make this. If it goes left, what happens to the concentration of N2? It will increase. Okay, and there we finished up section 6.